Okay, so Assalamu alaikum. In today's lecture, we will start the chapter number 9. Chapter number 9 is about the phase diagrams, right? Okay, so phase diagrams, I have sent you the notes, right? So phase diagram, phase means that material which has a unique composition, right? For example, if you have the alloy of nickel and copper atoms, then at one end you will see that the composition is different, and in the other page you will see the composition is different. So it is phase A and it is phase B. Just name it, right? Okay, so in this chapter we will combine two elements which resulting from equilibrium state. When we are given the temperature and the nickel or the copper percentage weight, then we can find out that how many phases are there, what are the composition of each phase, and what amount of each phase is present there, right? Okay, so now we can define the phase equilibrium, the solubility limit, right? So these are basically the related terms with the solution, right? So if I have a solution, for example, I have water and some sugar particles in it, right? Okay, so uh, the sugar particle is called solute and the water is called solvent, right? Okay, so solution is basically the homogeneous mixture, right? Homogeneous mixture. Okay, homogeneous means that if you pick a part from here or from here or from here and you test it in the laboratory, then you will comes to know that it has the same composition throughout the container, right? So it is called a solution. So a mixture and a solution are two distinct quantities, right? And a mixture is basically it has it is basically solution is its type. So the homogeneous mixture is called solution, and the non-homogeneous mixture is composed of two or more phases, right? Okay, so solubility limit is the maximum concentration of solute which can dissolve, right? So for example, what is the solubility limit for the sugar at a temperature of 20 degrees centigrade, right? So if we look at 20 degrees centigrade, right, then we see that only 65% of the sugar weight percent can be dissolved in water, right? This is a solubility line, and we say that it is a solubility limit line, right? So beyond this, there is only liquid, and if you increase the amount of sugar, right, then you will see that it will no longer be a solution. So there are two phases forming, right? And this line is basically separating these two from each other, okay? So if the sugar concentration is less than 65%, right, then it is a solution. But if you increase the solution, then it is the syrup plus sugar, right? Okay. Okay, so what is the difference between the component and the phases? So component is basically the element or compound that are present in the alloy, right? And phases, they are chemically distinct. I told you in the previous slide that it is a unique, right? It is a unique quantity which has its own composition. For example, when we dissolve the nickel and copper, then we see that there are two type of solids, right? So one is called alpha solid and the other is beta solid. So basically these alpha and beta are basically the different phases of the same solution, right? Okay, so now what's the effect of temperature on the composition? Okay, so uh, if we decrease the temperature from point B to point A, and basically this is again the sugar water solution, and the sugar composition is plotted on the x-axis, and the temperature is plotted on the y-axis, right? And this is my coordinate system. Sorry, this is y-x. Okay, so this is basically y-x, and here's the liquid, plus sugar, right? And this is the solubility line. So if we move from point B to point A, right, basically we are decreasing the temperature, then we see that we are basically moving from liquid solution to a different phase solution, right? We are entering from syrup to a two-phase liquid plus solid sugar solution. Similarly, if we increase the composition, the temperature is remain constant, but if we increase the composition of sugar from beyond the point B, then we see that we are also entering to the liquid plus sugar solution. Okay, so we see that the temperature and as well as the composition affect which phases are present. Okay, so in this course, basically you will consider the binary. Binary means two phases, right? So at most two elements will dissolve in each other for the binary alloy. And basically, if we plot the temperature and the composition on the x-axis for one element, and this is called the limiting element, right? So this is an example for the copper and nickel alloy, right? So at specific temperature above which there is a liquid and a specific temperature below which there is solid, and at some point here is liquid plus solid, right? So alpha is basically a solid which has FCC structure, right? And let me remind you that FCC look like this, right? It has one element in the phase, right? And we see that it is isomorphous, right? So you will see that the nickel and the copper are completely dissolved, right? So alpha phase extend from 0 to 100% with nickel, right? Okay, now phase diagrams. Phase diagrams basically told us that at which temperature and which composition which elements are present. For example, if you are given with the temperature of 11,000 degrees centigrade, 1100 degrees centigrade and 60% weight nickel, then you will see that on the x-axis, on the y-axis there is 1100 and on the x-axis is 6000. So if you meet this point, if you look at this point on the graph, then you will see that it lies in the alpha solid region. So you can say that at this instant here is only alpha solid, right? And if you are given with the 1250 degrees centigrade temperature, right? Temperature is 1250 degrees centigrade and the nickel weight composition is 35%. And you look at this point, right? So you will notice that it lies in the ELF, the liquid plus solid region. Okay. Okay, now we are given with the problem that you should determine the phase when you are given with the temperature and the composition, right? So in the first example, this is first and this is second, this is third, right? So you are given with the weight percent of nickel, which is 35%, and at 300 and 1320 degrees centigrade, right? So basically, this is 1320 degrees centigrade, right? And this is 35%. So if you join the vertical and horizontal line, then you will end up at this liquid phase, right? And if you move down with the temperature of 1190 degrees centigrade, right? So this is basically a constant composition line. And if you move down to this point, then you will see that there are two phases basically present, right? At 1250 degrees centigrade and at 1190 degrees centigrade, you will see that only the alpha solid is present in this solution. Okay. Okay, so the phase diagram, we can determine the weight of each phase, right? Okay, so if you are given with the temperature and composition, then you can determine the weight percent composition. Okay, so for example, if you end up with the point A, then you will see that the weight percent of the liquid is 100%, right? Because there is only one phase. And at point D, the weight percent of the alpha is also 100%, and the weight percent of the liquid at that point is 0. Similarly, the weight percent of alpha at 1100 at this point, right? This is 1320, it is 0 because there is no solid and there is no liquid at D point. But at B point, we have an interesting phenomena. We have the liquid plus the solid. So how can you determine these? Well, for this, basically we use the lever rule, right? Lever rule. Okay, so if I zoom out this section to here, right, then you will see that this is the liquidus line. Liquidus line means that above this liquid will start, right? Above this there will be liquid, and this is the solidus line. So you will see that below this all the composition will be solid, right? And in between there will be L plus alpha, right? So for example, if you end up at a point B, so this is my point B, right? So you will draw a tie line. You will extend from point B up to the liquidus line, and you will call this distance as R, right? And you will also extend this line to the alpha line, right? And you will call this distance S, right? So now if you want to determine the composition of the solid, right? So for the solid, you will write at R W of alpha equal R divided by R plus S, right? And for the liquid, you will write S by R plus S, right? Okay, so now determine what is R and what is S. R is basically the distance from point B up to the liquidus line, and on the composition, x-axis distance. So you will see that the R distance is basically here 35 minus 32, right? 35 minus 32. So it is basically 3. R is 35 minus 32 divided by, and what is R plus S? This is R and this is S. So R plus S is 43, right? And minus 32. 43 minus 32. So if you perform this calculation, then it will come out to be 27%, right? Okay, so since here are only two solids, right, two phases, so you can determine the composition of the solid as W alpha equal 1 minus 0.27, which will be 0.73, right? Or we can say it is 73%, right? Okay, so on this slide, I have explained the lever rule, right? So what is our lever rule? Basically, this is explaining that how can we determine the composition of the solid and the liquid, right? So you will see that this is the pivot point. Here, both the liquid and solid are balancing each other. So this is basically the R distance and it is the S distance. So if you take the moment about L equal to 0, then you will notice that W of alpha equal R divided by R plus S, right? And if you take the moment about this point, about alpha equals 0, then you will notice that W of L equal S by R plus S, right? So this is basically the lever rule, that how can, but the trick point is here is that you will consider the opposite direction, right? For example, if you want to determine the composition of the liquid, then you will consider this distance divided by this total distance, right? And if you want to determine the composition of the solid, then you will divide this distance. This distance is here R, and the whole distance is R plus S, right? And similarly, if you want to determine the liquid concentration, then you will divide the S divided by the total distance, right? So this is a trick here. It is basically opposite, and the composition has been explained here, right? Okay, so on this slide, if you cool down this copper and nickel alloy along a constant composition with respect to temperature, then you will notice that the liquid and the solid, how the solid is forming. Okay, so if I'm at point A, right? At point A, if we move out some portion of this alloy and you notice, you observe on the microscope, then you will see that all the composition is liquid, right? So this is liquid. Okay, so when you reach this liquidus line, right? So you will notice that these microstructures are forming. So this is basically the start of formation of the alpha solids. And when you go beyond the liquidus line at point C, then you will notice that these small particles of alpha solid, they are basically increasing, right? They are basically increasing in size. And also you will notice that the composition of nickel is also decreasing, right, in the alpha solid, and it is also decreasing in the liquid, right? But if you move to the point D, then you will notice that almost all of the liquid become the solid, and when you reaches to point E, then you will notice that it is all solid, pure alpha, right? Pure alpha. Okay, so it has the composition of nickel. Nickel is 35% here, and the copper is 1 minus 35, right? 100 minus 35, so copper will be 65%, right? So this is the final composition of the alpha. So you notice that how, with respect to temperature, the composition of the alloy changes, right? So there's basically a point for us that if we control this cooling, then we can form the structure which has a specific strength and which will affect its mechanical properties also. Okay, so that's it for today. See you in the next lecture. Thank you.